Hi, this is a lesson on partial derivatives. So here we have a graph of the function f of xy is equal to x squared minus y squared, or if you prefer, z equals x squared minus y squared. So here we have the x-axis is going in this direction. Let me just draw an x-axis in the middle, right there. We have a y-axis going in this direction. And then the z-axis is just going up and down, right there. So we're interested in asking the question, what is the rate of change? I should say instantaneous, actually. Instantaneous rate of change of z. Now, that's not enough, though, because it depends on the direction, doesn't it? Let's take a look. I graphed this in Mathematica here. Here we have the point x is 1, y is 1, z is 0 right there. So if I move in the x direction, you can see I'm moving upward. Z is increasing as x increases. However, if you turn this a little bit, in the y, here's y. In the y direction, actually, as y increases, y is going this way in the increasing direction, z is actually decreasing. And if you have other directions, you're going to have other slopes. And so we have to ask the question not only what is the rate of change, instantaneous rate of change of z, we have to ask in the x direction. Okay, so the notation for this, there's a couple notations I'll use. One is it's like a funny looking d, sort of a curvy d, dz dx, which is called a partial derivative of z with respect to x. Or you can also do this f and then a subscript x, meaning in the direction of x, of xy. So two different notations for the same thing. All right, so the main idea here with partial derivatives is, here's my point. I can see as x increases, z is increasing, but y is not changing when I'm moving in the x direction. So in other words, y is treated as a constant. Okay, so then it makes it very easy to find the derivatives, but I'm not going to do the derivatives quite yet because I want to first look at this on a contour plot as well. So here's the same graph. It's x squared minus y squared. I've got x is down here. Let's draw an x-axis right in the middle. Y-axis is right there. And here's the point 1, 1, right there. So in the x direction, moving in the x direction, I can see roughly my z coordinates are increasing. So this is 0. Every line is 5. So this is 5, 10, 15. So I can see that as x increases, it looks like when x goes up about maybe 2 points or so, z is going up about 5 points, roughly speaking. At least at that point there. So that gives me a rough idea of maybe just a guess. Maybe z goes up. dz dx is maybe 5 halves. It looks like I'm going up 5 units in the z when x goes up by about roughly 2, maybe 1. But again, it's just a rough estimate. Okay. Now y on the other hand, if I go this direction, the blue is going down. So this is -5, -10. And so I can see whatever dy dz is, that's going to be negative. Now, what exactly? Well, maybe -2.5 or something like that. Okay, but let's get to the actual definition now. So the partial derivative, I'll use the function notation here. So this says the partial derivative of function f in the x direction of x and y is equal to the limit. It's very similar to the definition of a derivative in 2 dimensions. It's the limit as h goes to 0 of f of x plus h comma y minus f of xy divided by h. Okay, so remember these are functions of 2 variables. So here's what's going on. If I were to zoom in, so at this point right there, I'm interested in the x direction. So here's my point 1, 1. If I move just a teeny tiny bit, like 1/1,000,000th of a unit or something, h units, h being some very, very small number, in the direction horizontally, how much is that z coordinate changing by? And so that, but notice that y is just y. If y equals 1, y stays 1. Actually, I put my point a little bit off. It should be about more like here, but anyways, you get the idea. Looks like going like that. All right. So you could, of course, do this the long way. Let's go ahead and do this one the long way. So I've got limit as h goes to 0. Okay, f of x plus h comma y. Well, that's going to become x plus h squared minus y squared, and then minus the function itself, x squared minus y squared, divided by h. Now, I'm not going to do the whole thing because you've seen this before when you took Calculus 1, but you see, first of all, those y squares are going to cancel. If you distribute that negative, you can see that becomes a negative x squared, becomes a positive y squared. The y squares cancel because y is a constant. Y doesn't change. So that makes sense it cancels in this case. Now, with more complicated expressions, the y doesn't always completely cancel out like this did, but it does in this one. You can see when you expand the x squared out, you're going to have limit h goes to 0, x squared plus 2xh plus h squared minus x squared. You can see the x squareds cancel, factor out the h, and you hopefully you can see this here without too much work because you did this exact same thing in Calculus 1. So factor out the h, I'm left with 2x plus h over h. H is cancel. I'm left with, and then replace h with 0, I get 2x. Okay, surprise, surprise. It's the same. It follows all the same rules as in Calculus 1. We have the power rule, chain rule, product rule, etc., etc. All those rules apply, except we're just counting that y as a constant. Okay, so now for the shortcut. So to follow the rule, so back to the original function, right there, x squared minus y squared. Here's what you do: is you treat, so step 1, treat y as a constant. And we know a derivative of a constant equals 0. Derivative of a constant times x or some other function is that constant times the other part, etc., etc. So all those rules you learned in Calculus 1, they all apply. And then step 2 is you take the derivative with respect to x. WRT is short for with respect to. Okay, so I've got, let me just use z here, a little bit quicker to write. So my original function, z equals x squared minus y squared. So dz dt with the curly d, meaning, excuse me, dz dx, pardon me, not t. That means the rate of change instantaneously at how much is z increasing with respect to x. So it's equal to the derivative of x squared, which is 2x, and then minus y squared, but y is a constant, so that drops out. So the answer is 2x. Same as we got doing it the long way, 2x. But now I can answer that question. What happens at the point 1, 1? So at the point 1, 1, 0, well, now you just plug it in. So x is 1, y is 1, z is 0, But in this case, my derivative has just x. So here's some notation. You may not have seen this before. So dz dx, you can put a vertical line and then just write the point down here. So this means the instantaneous rate of change of z in relation to x at the point 1, 1, 0 is equal to, and then you plug in your numbers, 2 times 1, which is equal to 2, right there. Using the function notation, you would write f, the derivative of x, the derivative of f as in the x direction at that point 1, 1. Leave the z out here, and that just would be 2 times 1, which is equal to 2. Okay, so that tells you that at this point, so back to our contour plot. I think it's easier on the contour plots. Actually, let me erase this because I had the wrong point, actually. It's the point x is 1, y is 1. So now I can see that in the x direction, the instantaneous rate of change at exactly that point, I don't have to do a guess anymore. I can say that it's now exactly equal to 2. That as x goes up by 1 point, z goes up by 2 points in that direction. And that kind of makes sense. I remember this is the average rate of change, but over roughly 2 units, z went up about 5 units. So my guess wasn't that far off. Okay, so how do you do dy? Excuse me, my goodness, dz dy. How do you do that? Right there. So ignore I wrote dy dz. That's wrong. It's dz dy. How do you do that calculation? Well, it's the same thing, but for the other variables. So to do dz dy, that means how fast is z increasing as we move in the y direction. So I can tell it's going downhill, first of all. You can see that from the original graph as well. It's sort of curving down a little bit on the other side as we move in the y direction. So same steps, but in reverse. So you step 1, treat x as the constant, and you take the derivative with respect to y. So let's go ahead and do that real quick. We have here dz dy. So the instantaneous rate of change of z with respect to y is equal to, well, back to our original function. So now x is the constant, y is the variable. So x, derivative of a constant is 0. Derivative of negative y squared would be negative 2y. So equals negative 2y. And so then at the point, dz dy, at the point 1, 1, 0, well, I'll just replace y with a 1. I've got negative 2 times 1, which is negative 2. So sure enough, it's negative, which we knew from the pictures. We know that as we move in the y direction, my function is going downhill. And so my answer is negative 2 at that point 1, 1, 0. I should write here 1, 1, 0. All right, and that is it for an introduction to partial derivatives. Now, of course, the examples get much more complicated. This was a simple example just to get us started, but there's other videos for that. So that's it for my introduction.